Welcome back, Unit 11. We'll be talking about acids and bases, Lesson 4 and pH scale.
That was horrible.
That was pretty pathetic.
That was so bad. Can you go back and do your
Where's the German
Schwarzenegger?
voice?
Just
Okay,
do your
okay.
Schwarzenegger, and that's it.
Welcome back to Unit 11, acids and bases, Lesson 4, the pH scale.
Woohoo!
So again, please be making sure you're reading up in the textbooks and your review books on these topics. And today we're going to be analyzing the pH scale, looking at it, and actually measuring pH. All right, so you guys will be needing calculators with you.
I like your background.
Thanks. You've seen Prometheus?
Yes.
It's with the alien movies, which is going with the theme of acids. Chavon.
So, what is the pH scale? I mean, you've all heard of it. You probably have seen it before in other classes.
It's a big thing in biology.
Yeah. pH scale is a numeric scale that basically talks about acidity to basidity
Or alkalinity.
or alkalinity of an aqueous solution. So we said anything that is less than 7 is acidic and anything greater than 7 is basic.
We know that pure water is neutral. If you guys watched the video that we posted on the self-ionization of water, you'll understand why it is neither acid nor base. Alright, so pH scale is an actual line, and that line we always number from 1 to 14. On the left, that is going to represent our acidic, so as you go from 7 to 1, you're increasing the acidic qualities. And as you go from 8 to 14, you are increasing in basic qualities. Okay, but if you notice at 7, we have an equal ratio of acids to base. Again, if you don't remember this, please look up the self-ionization video.
Anything below 7, you're going to have an increasing H ion. So as you go from 6 to 5 to 4 to 3 to 2 to 1, it's going to strengthen the hydrogen ion or the hydronium ion. Anything above 7 is going to increase the hydroxide ion. So as you increase from 7 towards 14, 14 having the greatest strength in hydroxide ions. Now that doesn't mean that the hydrogen ion's not there, it just means it's less than the hydroxide ion.
Another way to visualize this concept of the pH scale is by using colors. So in the middle, where white is, we'll call that neutral, because that falls right in the middle. On the far left, everything in red, that's acidic. That means we have more of our hydronium ions. And everything on the far right, which represents blue, is going to be more of the hydroxides. As you notice in the middle, neutral, there's the absence of color, so you have white. And if you go too far to the left, you become red. Too far to the right, you become blue.
Each change in pH value signifies a 10-fold change in hydronium ions.
And that's only going from 14 down to 1.
Right. So as you decrease it, every time you decrease it, it's going to be a 10-factor increase in hydronium ion. So going from 7 to 6, like we just did, it increases the hydronium ion by 10. Now we increased it another 10. So that's 100 now. So an example of what we just showed you is going from 6 to 5, we've increased the hydrogen ion by 10 times the hydrogen ions that was in 6. Moving from 6 to 3, because you're going down 3 different pH levels, that means 10 times 10 times 10, 1,000 times greater in the hydrogen ion. So a pH of 9 has 100 times less hydrogen ions than a pH of 7. That's because we're increasing the pH 2 times, so 7 to 8 to 9, which means that you're dividing it by 10 now. As you increase, you divide. As you decrease, you multiply.
So another example just to show you guys, using this color chart. Again, right in the middle, you're noticing that 0 on the far left-hand side. That's to tell you the difference in the comparison between the hydrogen ions and the hydroxide ions. So as you start to descend going from green into orange into red, you'll notice that the amount or the times difference of the hydrogen ions compared to water is going to significantly increase. But every time you go from one number to the next, going down towards 0, you only add on another 0, which is called a factor of 10. So every number change is an additional factor of 10. But do notice as you go towards more basic, you're now getting smaller and smaller and smaller quantities until you almost get into parts per million. So the pH concept is the idea that pH is a calculatable thing. So you do need your calculators for this, and you should probably look on your calculator to figure out where the log function is. But the pH is simply just equal to the negative log of whatever the molarity is of the acid. So when we examine the pH again, remember that monoprotic acids like hydrochloric acids only have one hydrogen that is formed. So you only multiply your concentration by 1. If you have a diprotic acid like sulfuric acid, your concentration is multiplied by 2. And if you have a triprotic acid like phosphoric acid, your concentration is multiplied by 3.
And that's only because you're going to dissociate the ions. So when you dissociate them, you have twice as many in sulfuric acid. In phosphoric, you have 3 times as many.
Mm-hmm.
Okay, so an acidic solution has a pH of less than 7, and the hydrogen concentration is going to be 10 to the negative 6th or greater. So 10 to the negative 6th, 10 to the negative 5th, and so on and so forth.
All the way down to 0. If you have any of these numbers when you look at your concentrations, then right away you know that this thing is going to be acidic.
A basic solution with a pH greater than 7 is going to have hydrogen ion concentrations of 10 to the negative 8th or lower, like 10 to the negative 9th, 10th, 11th, and so on and so forth.
I know it seems weird that we say lower because the numbers themselves physically are getting bigger, but when you have an exponent to a negative number that's really big, like 10 to the negative 14, that's incredibly small compared to 10 to the negative 8.
Remember to think of a number line.
And I know you guys are saying, what the heck? What do we need this for? I don't understand this. This is really hard. The exponent in this situation tells you the exact pH value of your solution.
So 10 to the negative 8th has a pH of 8?
Yeah. Oh. And if you have 1 times 10 to the negative 4th, you should have a pH of?
4.
Ah, that's pretty simple.
Yeah.
Okay.
Why do I need that formula then?
We'll be giving you guys different numbers eventually, and you guys will have to be calculating stuff from that. So again, just to reiterate the idea, when we have our pH of, let's say, 10 to the negative 7, as you notice, that's your pH value of 7, which is pure water. The exponent tells the pH value. All right, guys, so stuff you should have learned from this lesson. We talked about what is the pH scale and how we measured the hydrogen ions. We also talked about that increasing the pH level is a times 10 increase in concentration, while decreasing the pH level is a 10th of the concentration. And we should know that the calculation for the pH is equal to negative log the number of dissociated hydrogen ions times its concentration.
Which we'll practice in class.
Absolutely. But definitely make sure you have that formula written down in your reference table.
See you next time.
Bye-bye.
Welcome back to Unit 11!